conventional Theremin is a fairly simple device, at least looking at a 10,000 foot level. And I'd like to take a look at some of the details and some of the things that a guy can run into when dealing with a conventional Theremin, and then how one might use a infrared sensor, a wideband infrared sensor specifically, to try and address some of those issues, and also some things with digital processing that may make for a lower cost and a more user-friendly type of instrument, which is certainly a lot more customizable, or easily customizable, than having to sit and try and wind mixer coils and balance inductances to achieve the performance that you want. So with that being said, let's go in and take a look at some of the things in detail. As I mentioned in my other video, you have two oscillators. This first oscillator, basically this whole section serves as a tone generator, and the section over here, this serves as the amplitude controller, and then you've got an amplifier here and a speaker here to provide the audio output. But let's take a look at tone generation first. We've got an antenna on an oscillator, and the easiest way to think about that is if you got a really cheap AM radio. If you get it set up to listen to a weak station, you bring your hand next to it, it'll oftentimes cause it to drift and detune the thing, and that's in layman's terms, probably the easiest way to view a Theremin. Unlike trying to cause an AM radio station to drift, there's some games that are played here with the Theremin to make it musically pleasing and also practical. It's relatively easy to make voltage-controlled oscillator operate over a narrow range, a few notes or an octave, and you're good to go. And if you don't care if it's linear, i.e., that if you have your hand in one position, move it a half an inch, you change a whole octave, in one area, and maybe in another, you need to move your hand a foot. If you don't mind those type of things, it's really easy to do. You can throw a few transistors at it, and you're good to go. Now, in the old days, the vacuum tubes, those guys pounded their heads against the wall to make this thing playable, and some of the early advertisements talks about anybody can play this. Well, I think anybody can make sound with it. I don't know if you necessarily can be melodic, and but they wanted to get a decent tone, and they had to do a lot of game playing, I'm pretty sure, to make that happen. Especially vacuum tubes back then, there was a lot of variation from unit to unit, and even as vacuum tube science progressed over the years, consistency from tube to tube improved. But even then, if you wanted to have matched tubes for a given application, you still had to have adjustments, because it's darn hard to physically control all the manufacturing processes to make things identical from lot to lot. Yeah, I was involved with some little bit of vacuum tube envelope manufacturing in my early days, and it's an interesting challenge. But anyhow, let's take a look at this. We have a reference oscillator and a main oscillator, and they're in the original design. I think they're running around a couple hundred kilohertz, and they run into a mixer. And if they're both running at the same frequency, the output of your mixer is going to be about 0 hertz. Because what happens out of mixers aren't perfectly. If you had a perfect mixer, you'd put in one frequency and put in another frequency, and you would get the two. In a perfect world, you just get the difference between the two. But that's not nothing's ever perfect. Well, I guess you could do it digitally, but that's another story. But what happens is not only do you get the difference frequency, you get an additive part that comes in there, and mixers you don't get a perfect sine wave out of the thing either, and of course the oscillators aren't perfect in their sine wave, and the net effect of this is you end up having your spectral content change depending what note you're at, and that's how it ends up being pleasing to the ear versus some of these hey, build a Theremin in an afternoon. Yeah, you can do that, but it's probably going to sound kind of cruddy because you're not going to get the same spectral effects and the harmonics as the frequency changes. So they did a lot of game playing around to pull this off using just 1 or 2 tubes and a whole pile of inductors and air coupled transformers to pull it off. And as you can see, after the mixer there's a filter. I think I mentioned that a mixer will output the difference between the 2 frequencies, also the additive of the addition of the 2 frequencies, and it'll also have some leakage from the initial oscillator and the reference oscillator. Now, granted, they're 200 hertz, so if you get some of that leakage in there as it goes through the system, you're not going to be able to hear it anyhow. But we also have other things going on. If we go and look, we have oscillator number 2, which is our amplitude controller, runs through a voltage controlled amplifier and then through a regular amplifier to drive a speaker. There's some coupling and interaction between everything here. I mean, you try you obviously don't want to have the playing around with the amplitude antenna throw the main oscillator and the pitch way out of whack. But there is a small amount of coupling, because you do have some of oscillator 1 is going to make it through the filter, and you're also going to have some level of induced coupling just between these 2 oscillators and even the antenna. Now, it's small, but these things all contribute a little bit to the harmonics and the makeup and the pleasant sound of it. Which is why, again, build a Theremin in an afternoon, and it probably isn't going to sound anything like what you hear in the classic recordings, because you don't have the well, I mean, you could maybe get real lucky, but throwing transistors and op amps into a circuit without doing a bunch of tweaking to try and get some good sound out of it, that's a tricky deal. And the other thing, in the ideal world, you'd like to be able to have more than a couple octaves of range. I mean, it'd be really cool if you could go from a low E of around 34 hertz all the way up to the kilohertz region for your high frequency stuff, and have decent tone throughout that range, and also have it linear, so that you didn't have, if you moved your hand half an inch, maybe you might go through 4 or 5 semitones in one area and move it half an inch in another area and get 4 or 5 semitones. You'd like to have that be reasonable, and they did a pretty decent job of that with the vacuum tubes. But in an afternoon, you're not going to get that. Maybe you'll get it linear over an octave, maybe 2, and then it'll get really goofy at the end of the range. And it's just a similar deal with the amplitude control over here. Is you don't want to be sitting there going, oh, it's real soft to real loud in a 1/4 inch. You'd like to be able to vary that around as your hand moves. And again, with the guys that spent probably gazillions of hours tweaking and adjusting their designs back then, they did that. You could certainly do this, come close with transistors, but I think you'd have op amps up the wazoo to try and match the spectral characteristics of an older unit. And one of the things that this all brought to light is, I thought, well, instead of sitting here with the antenna and getting these oscillators and trying to keep everybody happy, I thought, let's take a look at using wideband infrared. Specifically, the sensors that I've chosen, they operate around, they start turning on around 8 to 9 microns, and they go out to about 14. Now that's a fair area of the long infrared part of the spectrum, and it's ideal for picking up skin temperatures. And the way that the sensor operates is it basically measures your skin temperature relative to what the background temperature is. So if you're in a really hot room, this infrared Theremin using wideband IR isn't going to work worth a hoot. But if you're in a room where you know, your hand temperature is typically for anywhere between 88 to 93 for the average person. Room temperature is, you know, 65 to maybe 75. That's enough to get a decent signal. And by playing with the optics, it's possible to have, as your hand moves into view, you get into view of the sensor, you get a reasonably linear output until you're, you know, totally covering it. And if you're real close, you have 100% coverage. And as you move further and further away from the sensor, raising your hand, the amount of energy emitted by your hand compared to the energy that's being emitted by the rest of the room decreases. And it's a matter of balancing the optical train, and unlike when I used to design industrial devices, we wanted to have nice sharp cutoffs so that if there was some thermal event going on just outside the sensor's field of view, we wouldn't pick it up. Well, when I'm trying to do this, I want to have linear motion of the hand creating a linear voltage. One of the ways in which I did that was making the edges very, very blurry. Rather than, if you think of a boxcar shape, is an ideal thing, and normally you want to have that close to that in an optical design. I tried to make it a trapezoid, and it's got some nice edge effects, which, you know, in normal situations would be absolutely terrible. But in this particular situation, it does tend to lend itself to be linear. And the advantage of doing that, if we run it into a single board computer, we can get by with an onboard 10-bit A to D. If it was very nonlinear, we might have to go to 16 or even 24 bits, and then we don't get any speed out of it, and then we're pulling our hair out because, you know, you can maybe change a note every half a second, and that defeats the whole purpose. Now, the other thing with the single board microcontroller, if we look over here, we could then drive a USB interface, and as I mentioned in my previous video, we can also emulate make a virtual MIDI port right on this microcontroller to drive the USB interface to go right into your computer. But we can also tap off the serial data off the microcontroller and do a little bit of level shifting and throw an optocoupler in there, and we can put a 5-pin MIDI port on it. And if we've got enough RAM space, which this would probably require assembly, we could even throw a waveform generator. The Arduino has a Mega 328 microprocessor, and there's a lot of code space if you write in assembly. And you could make a pretty impressive waveform generator. Have it drive a DAC though, rather than you know, trying to use PWM if for no other reason to save processing time, because trying to send Theremin data via MIDI is tricky, because what you have to do is try and emulate the pitch shift wheel, and then make transitions from note to note in order to you know, have a nice glissando sound instead of you know, type of, with all kinds of steps in there. So we need to make sure that if we are doing MIDI, that we're careful in handling the data stream. So I was saying we'll use a DAC, and then we just have a buffer on the DAC, and we can drive an audio connector, you know, use a 1/4-inch jack, plug it into an amplifier mixing board. And if we also have you know, the single board computer, we can stick a user interface and an LCD display, because there are calibration issues, especially, you know, room temperature varies, and some people, their skin temperature varies a bit, or from user to user. One guy I used to work with, his skin, we used to call him, he was, you know, cold-blooded, because his skin temperature was only maybe 10 degrees above room temperature. And for him, he couldn't play a wideband IR Theremin, but he was kind of an exception to the rule there. Again, this is all, you know, it's a goal, it's a blue sky type thing. And one of the things, I guess, you know, you can see here, I'm zooming in, you can see some more of the details, and the text is a little easier to see. Um, One of the things I thought of is, instead of just having the an amplitude sensor and a single sensor for sensing pitch, one could have an array of sensors and an amplitude sensor, and you could not only control pitch and amplitude, but also filter functions, or with a little bit of creativity and tweaking your software, maybe even make up something like an air piano where you've got a limited amount of the ability to do multiple tones at once. Now, you obviously can't send your MIDI data stream is sequential, so there's it's technically not all at once, but from an ear standpoint, we can process the data between sending MIDI data packets so that we can have multiple notes appearing to the human ear to be going on at one time. This is sort of a humongous goal, after the basic system's up and running. But that's sort of the whole thing is I'm building some sensors, playing around with the optical trains, and trying to make a ineffectively an open hardware infrared musical instrument. That's where I'd like to end up anyhow. Thank you for listening.